Okay, everybody, welcome to IPAC 2025. This is our fourth year of it. And we're going to be presenting different papers, usually 3 to 6 lectures per paper, and kind of recent important papers. And the format here, if you haven't been before, it's more informal than a typical conference talk. So feel free to interrupt anytime to ask questions, and you can also, of course, put questions in the chat. Okay, so without further ado, our first speaker is Maria Gillespie from Colorado State, and she is giving some talks on a combinatorial skewing formula for the Rise Delta Theorem, which is joint with Sean Griffin and Eugene Dvorsky, and they have also another paper on this related to this and the delta conjecture. And then Sean will be giving 3 lectures on that paper after Maria gives 3 on this paper. So take it away, Maria.
Okay, thanks for the introduction, and thanks so much to the organizers for having me here. I'm really excited to be speaking at IPAC because I've been a fan of this sort of summer workshop for the last however many years it's ran. And yeah, so I'm going to be talking about some new formulas we found for the delta theorem and the polynomials involved in that, both combinatorial and algebraic. And then Sean is going to be talking about the sort of geometric side. So I'll outline that in a bit. And I just wanted to start like backing up a little bit to some of the motivation from the shuffle theorem and other things in symmetric function theory. So yeah, as Jim said, please feel free to interrupt with questions, especially in the chat. I have the chat open so I can see questions popping up, and I will try to answer things live. I've sort of organized my notes so that I'm going to be filling in things, but it's sort of partial notes, and so this way I won't have to write too much, but hopefully it'll still be understandable. So first we're going to start with some background. So the shuffle theorem is or it used to be the shuffle conjecture. It was proven by Carlson and Mellett, and it's a formula for a symmetric function nabla en, which nabla is an operator on symmetric functions that we think of as a Macdonald eigenoperator. So if you're familiar with Macdonald polynomials, we won't need them for this talk, and we don't need the definition of nabla either. But it's some operator that operates on symmetric functions, and it scales the Macdonald polynomials, which are a basis, and so then you can extend this to an action on any symmetric function, including the elementary symmetric function en. So I'm going to just define the symmetric function en. This is the elementary symmetric function in infinitely many variables x1, x2, x3, dot, dot, dot. Now, we will, in this talk, at some point be restricting to a finite number of variables, but not yet. For now, E3 means x1, x2, x3, plus
I'm sorry,
x1.
you're not screen sharing.
I'm not screen sharing?
No, I see you fine, but I'm not seeing it
I
right
thought
now.
I shared my iPad screen. Does not.
I see the screen.
I can see.
I see this.
Me too.
This is the screen. Yeah.
Oh, really?
Okay, Jake says I think the screen sharing is working fine. Does everybody see like my red writing and things like that?
Yeah.
Yep.
Yeah.
Okay.
Dale, maybe you can see on the top of the Zoom. Maybe you can see Maria, like that's another share screen. Maybe you can click on that one. I think that's a setting on the Zoom thing.
Yeah, if you click on my iPad one, there's 2 Maria Gillespies probably, and the one that's my iPad will have the screen shared. So maybe if you click on that one, it'll help. Yeah.
There's an option for swapping video and shared screen. That makes the shared screen disappear under the view menu.
Okay. So maybe you have to click your view settings. Okay. Should I go on? I don't.
Yeah.
I don't
Yep.
leave anybody behind. Okay. Sounds good. So we have basically the sum of all products of 3 distinct variables. So you're not allowed like x1 cubed, or I'm going to cross these out, or x like 5 squared, x6 or something like that. You're not allowed a squared term or a cubed term. You're only allowed 3 distinct variables. So it's homogeneous, but it's all possible products of 3 distinct variables all added together. So, you'll have x2, x3, x4, and it's an infinite sum. So you'll also have things like you know, x17, x100, x2000, right? And it just goes on forever. So that's the elementary symmetric function E3, and you can think En is the same thing for n variables in each monomial. And so then you apply this Macdonald eigenoperator, and the shuffle theorem says that we have something on the right-hand side that's this beautiful combinatorial formula in terms of parking functions. And parking functions are a column labeling of a Dick path. A Dick path is a path in the unit grid that goes up and right and stays above the diagonal y equals x. So here's the diagonal line here, y equals x. And then here's our path above it that stays above the diagonal, right? It stays weakly above the diagonal, so it can hit the diagonal, that's okay. And then you label the columns, meaning the up steps. You label the up steps as you go up with numbers, where in each column you have to be strictly increasing, but you can have repeats across different columns. Like I have 2 1s in this labeling, and maybe I have a 2 there. So I've assigned a label to each up step. This is a labeled Dick path. And you're allowed repeats. And so some people write this in terms of quasi-symmetric functions, but I'm here just using monomials and just allowing for words, meaning repeats are allowed in our parking function. And so that actually makes it a symmetric function as well. The x to the pi over here just means you take your x variables, and basically every time a 1 comes up, you have an x1, so you would have x1 squared. That's how many times x1 shows up. I think there's a bit of a lag from when I write to when it shows up on the screen, so I'll make sure I pause sometimes. And then I have 2x2, so I also have x2 squared, and then I have an x4. And so I'm just recording all of the entries of the parking function as a monomial, basically. So this is going to be a very common thing we do throughout this talk. And so that's how we make a monomial out of a labeled combinatorial object. And then we have Q and T. What we're doing is symmetric functions with coefficients that have Q's and T's in them, and they're just parameters, really. And we have area of pi and div of pi. These are just combinatorial statistics. I'm just going to write that down. We're going to define these later. But for instance, area is the number of squares that are below the Dick path but above the diagonal. So like these squares, right, would be the area, would be 4 in this case. And div is something measuring sort of inversions between the labels. So we'll define those in more detail later. I'm just doing an overview for now. Okay, so then the shuffle theorem, not only is it a beautiful combinatorial formula for a nice operator applied to an En, it also has geometric connections. So it's motivated by affine Springer fibers, which Hikita found a connection between nabla En and affine Springer fibers. And there's also a connection to Hilbert schemes due to Mark Heyman. And that one is sort of intuitive because this comes from the Q and T really kind of record what's happening intuitively in the plane, where you have your x-axis and y-axis, and the Q and T somehow record what's happening on each axis. And the Hilbert scheme in question is the Hilbert scheme of n points in the plane. And so you imagine n points in the plane, and Q is like the x coordinates and T is like the y coordinates, and you have, you look at the Sn action on these points, and there's, there's connections to diagonal harmonics and a lot of interesting algebraic constructions as well. So I don't have time to go into all those connections, but this is just sort of a background on the shuffle theorem, which is something that the delta theorem generalizes. So this is sort of where it's coming from. And now we're actually going to look at 2 generalizations of the shuffle theorem today. Okay. So the first generalization, let's zoom in on delta. So we're going to generalize this nabla operator. And Jim Haglund, who introduced me, was one of the people who was on this paper. Haglund, Remmel, and Wilson introduced these delta operators, delta F, and basically because they looked like they had nice similar properties to the shuffle theorem, and they did. So the delta operators are defined for any symmetric function F. And in particular, this nabla is a specialization by saying, well, like nabla En from the shuffle theorem is delta En minus 1 applied to En. So En minus 1 is just, another elementary symmetric function, and you generate an operator with it, and you apply it to En again. Then in terms of the delta conjecture was, what is delta Ek applied to En? right? And there's conjectured combinatorial formulas for it, and one is proven. And for this talk, we're actually going to be using a slightly different notation that's also from the Hagelin-Remmel-Wilson paper, delta prime EK EN, which if you add delta prime EK EN and delta prime EK minus 1 EN, then you get delta EK EN. So in other words, in order to understand this delta function that is the key player in the delta conjecture, it suffices to understand these delta primes of some, elementary symmetric function applied to another elementary symmetric function.
But then
So,
how,
so that's what
how
we're
are the delta
focusing on.
primes defined? You have to define something
I'm not
else.
defining any of these things, actually. I'll be defining them actually in the second lecture. I think we'll have the first definition of what these things actually are. And I'm only going to be using really the combinatorial formula that comes from the Rise Delta Theorem. So I really I'm trying to summarize this paper and give background on what these are. And I mean, maybe I'll just say they're very similar to this formula with you sum over parking functions and of some sort, and there's an area and dim statistic and a monomial, and you add them up and there's a nice formula for these. So they're all in this big family of symmetric functions that have nice combinatorial formulas. Okay. So there were two formulas conjectured, the Rise formula and the Valley formula. And so these are two combinatorial formulas for delta EK EN. And the Rise is now proven in what I'm going to call BHMPS. This is really Blasiak, Heyman, Morse, Pun, and Pun is here too. So now we have the two organizers have already shown up on my second page here, and Seelinger. And I'm going to refer to BHMPS quite a lot in this talk because we build on their work quite a bit. So the Rise formula is proven. The Valley formula is still open. And so you can take a look at that paper, the BHMPS paper, if you're curious about what these formulas are. And one interesting thing is, even though there are, clear geometric connections of where nabla EN come up in affine Springer's and Hilbert schemes, it's not as clear, it wasn't as clear what the geometric connections are for the delta conjecture. And that's what Sean is going to be talking about in after my 3 lectures, whenever it is, 2 weeks or something. Sean is going to be talking about a geometric interpretation we found that for the delta polynomials. Okay, and so there's two things that we're going to connect that generalize shuffle, delta and rational shuffle. So the rational shuffle theorem is another variant of the shuffle theorem due to Bergeron, Garcia, Levin, and Jin. And Mellet proved a lot of these formulas. And so kind of all of these authors together. And basically the operators now are coming from the elliptic Hall algebra instead of being these delta operators. So different operators, and you can construct it algebraically, but there's also combinatorial formulas involving now rectangular parking functions, where now you have to stay above the diagonal like this in a rectangle, and you don't have to be in a square. So here above in the shuffle theorem, we had to stay above the line y equals x for a combinatorial object. I scrolled up and it's lagging. Okay, so there's line y equals x, just the diagonal line. So you're basically constrained to a square for this case. But what if we just make that square a rectangle and still stay above the diagonal, right? So going back down to the rectangle, then we'll have, again, some kind of, labeled parking function thing like this. And you would, get a monomial the same way. And so, yeah, maybe I should just pause. Does everybody understand how I'm getting these monomials? Because that's pretty key. So, okay, I see some thumbs up. Any questions? I'm not going to put down the formula for rational shuffle yet either. That's going to be third lecture. So, okay.
Is it important to know why there's no number label underneath that top 3?
Oh, because I missed one.
Oh.
Because I missed an upstep. And okay, now thank you. See, I wanted to pause especially because I probably made a mistake by now. Okay, now Kyle, you can tell me. This is my student, Kyle, everybody. Kyle, would you like to tell me what the monomial should be now that I added a 2 there?
X1, x2 cubed, x3 squared.
Thank you. There we go. Because we have 3x2s and 3 2s and 1 1 and 2 3s. So we record those in the exponents. So okay, so now I want to give a big overview.
Can I ask you a quick question before you
Yes.
go on? Can you say again, I kind of missed it. So there's one set of names right next to rational shuffle, and then you have mellet sort of down below. What's the sort of different references there? Oh, proof. Okay.
Yeah,
I see.
the formulas
Okay.
were sort of created. I mean, it's sort of
I
like
see. So okay.
Hagelin-Remmel-Wilson. It's a Hagelin-Remmel-Wilson versus BHMPS. Hagelin-Remmel-Wilson is to BHMPS as BJ as the other two are as an analogy.
Okay. Thanks.
Yeah.
Thank you.
Yeah. Thank you for catching that. Okay, so I'm going to give a high-level picture of the next 6 lectures, not just my 3, but also Sean's 3 lectures, and what the big picture is, because really our 2 papers were companion papers that go together, and all of it were by me and Sean and Eugene. So in the middle, we have this skewing formula, which is the main theorem that I'm going to be presenting today, and we're going to basically outline the proof of the thing in the middle today. So it's a skewing formula that relates the delta side, this delta prime ek minus 1 en, to the rational shuffle side, which looks like this operator coming from the elliptic Hall algebra, e big K comma little k, applied to 1. So this is the rational shuffle side. And they're related by this S of a rectangle perp. So I'm going to define the S perp operator in detail. We'll go slowly through that. But basically, you're going to apply an adjoint Schur function operator to the rational shuffle, and it actually spits out the delta polynomials. So this is relating these 2 generalizations of shuffle together with one single operator. So that's the main theorem. And what we're going to do is use this rectangle that I have in the Schur function is just the k minus 1 by n minus k rectangle. So we're going to fix that rectangle throughout the talk. Sometimes we'll transpose it, but for now, that's what the rectangle is. And this big K here in the rational shuffle is related to the little k and little n over here. So you basically have 2 parameters on both sides, little n and little k, that are defining everything. Big K is little k times n minus k plus 1. And we'll see how big K comes up. But basically, in the rational shuffle case, we're actually going to be working in a different rectangle. So it's a little confusing because we have 2 rectangles. We have a big K by little k rectangle, and this is going to be the one we draw the dict paths in and have the diagonal like that, like shown on the previous page. Whereas this other sort of k minus 1 by n minus k rectangle is just the one that we use the adjoint Schur operator to apply to the rational shuffle to get the delta. So 2 important rectangles in this paper. And notice that in this rectangle over here, we defined big K to be a multiple of little k. So this is the non-coprime case where the height is actually divisible by the width. So the diagonal is going to sort of run through a lot of the grid points here. Okay, so we have this skewing formula. That's our goal. And so let me say what Sean's going to do in the 3 lectures after me is so come back on June 12th, 17th, and 24th to see how we found a geometric interpretation of the Rise Delta formula using affine Springer fibers. Well, actually, it's a generalization of Hikita's affine Springers that we call affine delta Springers, which is just going to be a different construction that is, you take Borel-Moore homology and you have 2 SN actions and you take the graded Frobenius and it spits out this QT symmetric function. So he'll go into that in 3 lectures. And what I'm going to do is down here, so this will be my June 3rd lecture, is an algebraic proof of this skewing formula starting from work of BHMPS, their proof, and also the Mellet proof on the other side. So basically combining the 2 proofs of the 2 sides, using tools from that to show that the skewing formula holds. And then on the next 2 lectures, so if you're a combinatorics person and you don't want to see a bunch of operators, come back for the next 2 lectures after this one, because on June 5th and 10th, I'm going to be going through a combinatorial proof of this result. And what do I even mean by combinatorial proof? What I mean is take the two formulas for these in terms of parking functions. So the one for the delta polynomial, I'm going to go into a little more detail now. There's these things called stacked parking functions. And there's also an area formula and a div formula, but it's called hdiv now. And you take, this is one combinatorial formula for delta. For rational shuffle, the formula also looks similar. It's a sum over all word parking functions of this big K by a little k rectangle. And you take another area statistic, basically defined in the same way, and then Q to a very complicated inv statistic that's going to take like probably half a lecture to define, and then, sorry, x to the pi. And the combinatorial proof is the idea of how can we take these two combinatorial formulas and understand how to apply a sure skewing operator to get from one to the other with some bijective proof between these statistics, right? And so what we're going to do to simplify it a little bit is use decomposition to LLT polynomials and lots and lots and lots of combinatorial analysis of these dim statistics, which was the hardest part to get a handle on. And there's going to be a beautiful sign reversing involution that we're going to play with as well. That's kind of the key step. So there's going to be some, LLTs and cancellation and showing these two sides are equal just from a combinatorial perspective, which is really fun because it's going to link together all the combinatorics that comes in from both sides. And if you think about it, really this algebraic proof plus the combinatorial proof can be thought of as, okay, if we do the algebraic proof first and we have this skewing formula, and then we say we only have rational shuffle, we start on the right-hand side, we can think of this as a new proof. The combinatorial proof really gives us a new, I'll just say combinatorial / algebraic proof of the Rise Delta Theorem, right? So it's just a little more combinatorial. Starting from rational shuffle, you can get to the Rise Delta formula, or vice versa. I mean, really, it's sort of either or, because we're showing the skewing formula holds combinatorially as well. Okay, so that's the big outline, and I sort of wanted to orient everybody before we really dive into the details. So I know there's a lot on this page. So any questions before I go on?
So when you combine the two, are you like doing the algebraic stuff and applying combinatorial techniques to it, and then you're also doing it the other way around, or?
When I say I'm combining the bottom two circles to get the new combinatorial proof, I just mean that it's sort of like a technical way you think about the direction that the logic goes. Because if you've done the algebraic proof first, then you just assume this skewing formula is true. And then you go through the combinatorial proof of the skewing formula. What that's actually doing, if you already know the skewing formula, is just like if you pretend you didn't know this formula on the left, but you knew the formula on the right, then you can do this combinatorial reduction to get the formula on the left like spit out. So actually it gives like basically another way to derive the delta formula, the Rise Delta formula, if you didn't know it, I think is kind of what I'm implying here. And it's just like a matter of, we have so many different proofs now, you can like start from whichever one you want, and like then the other ones will tell you the formulas or whatever, it depends how you interpret it. That's all I'm saying.
Okay.
Yeah. Okay. So we're going to dive in on this middle circle. We're just going to prove the skewing formula today, or as much as we can. The algebraic proof strategy is basically reduced to k variables. So we have this infinite symmetric function ring that we usually work in x1, x2, x3, ... And our coefficient ring our coefficient field is q adjoin q and t. So we're using q and t as just formal variables, and we're allowing rational functions in q and t. But then we want to restrict to k variables sometimes and just use symmetric polynomials, right? So sometimes even we might have just two variables, and we would have like x1 squared x2 plus x2 squared x1. That's a perfectly good symmetric function in two variables. And there's a projection map pi k from the full symmetric function ring to lambda k formed by just setting all but the first k variables to 0. So if you have f of x1, x2, ... You would just map that to f of x1 through xk, and then all zeros. Okay, So I think a lot of people in this audience will know the elementary basis and stuff for the symmetric function ring, but I want to also go through. Excuse me one moment. My kid is here. Yes. Sorry about that. So we have, what I'm going to do now is define all the bases for the symmetric function ring, but also note what they are for k variables, because we're going to be using that a lot. So the elementary symmetric functions, these are all defined for partitions lambda with decreasing parts lambda 1, lambda 2 up to lambda r. And the elementary symmetric function e lambda is the product of the e lambda i's, where any individual en is the one we defined before. So like e21 is e2 e1. And for instance, in 3 variables, we would just do x1 x2 plus x1 x3 plus x2 x3, and that's it, because we only have x1 x2 and x3, and then we would multiply that by e1. So the other ones are defined similarly. We have h lambda 1 through h lambda r, and h2 is the complete homogeneous symmetric function. So this one is the homogeneous symmetric functions are defined by adding up all the monomials of degree d for some d, in this case 2. If we have 3 variables, this would be the complete homogeneous symmetric function h2. And then the monomial symmetric function defined for lambda is just the sort of minimal symmetric function containing the monomial that has lambda as its exponents. So like x1 squared, x2 to the 1, and then you add all symmetric terms. So x1 squared, x3 plus dot, 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 right? So we have elementary homogeneous monomial, and then we need the most important basis is the Schur functions. And so to recall the Schur functions, these are S lambda is the sum over all semi-standard Young tableau of shape lambda of the monomial x to the t, which is defined the same way as in the Parking functions, which is why I emphasized that monomial. So for instance, S221 would be defined as follows. You draw the Young diagram of the partition 2, 2, 1, which I'm drawing in French notation, so stacking 2 boxes on the bottom row, then 2 above that, then 1 on the top. And you fill the boxes with some numbers so that they're increasing up columns like the Parking functions were, and they're weakly increasing across rows. Sorry for the skipping. Okay. So for instance, we could fill it with 1, 1, 2, 2, 3, 3. So they're weakly increasing this way and strictly increasing up that way. And we would get the monomial. There's 2 1s, so we do x1 squared and then x2 squared and then x3. And same for the next one. Right. So I'm going to just draw 2 tableaux here, and I have 1 1 and 2 2s. Oops. And x and a 3 and a 4. If you have only k variables for Schur functions, what that means is that you only have the numbers 1 through k to put in the boxes, and so that restricts your height to at most k, because if I have, say, only 3 variables, then I can't go more than height 3. There's nothing to put in this box, so it has to increase. So you can't have height 4 if you only have 3 variables, so the length of the partition, meaning the height of the Young diagram, is bounded by k, and so S lambda for those length of lambda less than or equal to k forms a basis for lambda k. So we're only going to be using those Schur functions. Now, skew Schur functions, because this is a skewing operator. Why do I call this a skewing formula? Because the adjoint operator makes skew Schur functions. So a skew Schur function is formed by taking 2 partitions, lambda and mu. Mu fits inside lambda, and you cut out mu from the Young diagram of the big one, lambda, and you fill the remaining boxes with some numbers. Again, in a way that they're increasing going to the right, weakly increasing going to the right and strictly increasing going up. And so you would have, your same monomial here, something like that. And you would do that in all possible ways and get some symmetric function. So we're going to be using skew Schurs as well, because this gives us a formula for what this adjoint operator does. So we can finally define, we're going to focus on what this adjoint operator S lambda perp is. And the way to define it is using the Hall inner product, which is the inner product on symmetric functions that defines the Schurs to be orthogonal to each other. The inner product of S lambda and S mu is delta lambda mu, which is just the indicator function 1 if lambda equals mu and 0 otherwise, if they're not equal. When we restrict to k variables, it's the same thing. It's still delta lambda mu, but you're just looking at only the basis that that actually doesn't vanish, right? Where the length of lambda and length of mu are both less than or equal to k. And so you extend linearly to the entire ring. Okay, so then these adjoint operators are just adjoint to multiplication by a Schur function. So we have S lambda perp mapping lambda to lambda, and also S lambda perp k, being the restricted map on the lambda k, which is restricted to k variables. And I just want to point out there's a little commutative diagram you can actually draw here where these are compatible with the projection maps, right? If you project the operation of adjoint for S lambda, it projects to S lambda adjoint for K. And these are defined by the inner product of F with S lambda times G is the inner product of the adjoint operator applied to F inner product with G for any two symmetric functions F and G, and same thing for here. So it's just left adjoint to multiplication. This one's left lambda perp K. Because we're using the K whole inner product. Okay, and then the fact that we can use here to relate the perping to skewing is the Littlewood-Richardson rule, which can be stated in many ways. And one of the ways to look at it is the inner product of S lambda with a product of two Schur functions, S mu and S nu, is the inner product of S nu lambda skew mu with S nu, and these are both equal to the Littlewood-Richardson coefficient C lambda mu nu. So this is called a Littlewood-Richardson coefficient. And there's a lot of fun combinatorial formulas for Littlewood-Richardson coefficients. We won't need them. It's just a a famous formula in algebraic combinatorics. So for instance, S mu perp applied to S lambda, then because we sort of moved this S mu times and S nu, the mu kind of moved over to the left and got skewed. What that means is the adjoint operator to multiplication is actually skewing. So the way we apply a perp operator to a Schur function is just by skewing that Schur function by the perp operator. And so in particular, if you applied S mu perp to an entire symmetric function that's written in terms of the Schur basis with coefficient C lambda, then you just apply that adjoint operator to every one of those Schur functions, and you get a formula in terms of skew Schur functions, which then these can be broken up into, actual, regular, sorry, what do I want to do? Yeah, into ordinary Schur functions that aren't skew using the Littlewood-Richardson rule. So applying adjoints is pretty easy when you have an expansion in terms of Schurs, but we want to apply this adjoint operator to the rational shuffle to get the delta, and there's a snag. So I put I'm waiting till it scrolls down here. I don't know if people can see it scroll down. There we go. The snag is that we don't have Schur expansions for either side. So it would be really nice if we had a Schur expansion for EKK of 1, because then we could just apply this skewing formula and skew all the Schur functions and show it's equal to the right-hand side. And I need peace and quiet here. Hi, you want to say hi? Okay, you can go out in the back, okay? Okay, close the door. Okay, so
Why can't you just generalize what you have up there to rectangles?
You can. The problem is that so yes, mu can be a rectangle. I'm gonna put a box around mu there on the top formula on this page. So mu can be a rectangle if you want, and that's fine. The problem is that this formula here for how to expand only works if you know the decomposition into Schur functions, which always theoretically exists. So we could like plug it into a computer for any given k and k and say, okay, write this in the Schur basis, apply this perp operator, just skew all the things, expand it out. Is it equal to the right-hand side? And that's how we tested it, right? I mean, it's easy to sort of computationally apply a Schur skewing operator because of this formula. But to prove that this works in general, we don't have a combinatorial formula, for instance, for the Schur expansion of either rational shuffle or delta. And so we can't just like naively apply the way we would usually skew things. Does that make sense? Cool, thanks for the question. Okay, so what do we do instead? Well, we apply the omega involution, which makes some things better. The omega involution takes a Schur function to its transpose, and the transpose just transposes a diagram like this, where you reflect a Young diagram about the main diagonal. Wait, I didn't transpose that correctly, did I? Oh no, I really didn't. Here, I just geometrically did not flip it. That's better. Okay. So applying omega to a shear function transposes the shear function, and applying omega to an elementary symmetric function turns it into a homogeneous symmetric function. And it's also worth noting that it's an involution that's also an isometry for the whole inner product. If you apply omega to both sides, you just get the inner product of FG. So once we apply that omega involution, we're going to just fall back on things that have been previously proven. In these papers, you can show that omega applied to the things that we want, EKK of 1 and the delta side, they only use shears with length of lambda less than or equal to k, which means it suffices to reduce to k variables to prove it. So even though we don't have the expansion, we know that there won't be any other shears involved. And so then we can reduce to k variables, and the advantage of reducing k variables is then we can use the power of GLK representation theory to get a handle on what this adjoint operator is for k variables, which it behaves a little bit differently than for infinitely many variables. And so we're just basically reducing all our algebra to k variables now. Let me see how I'm doing on time. Okay, so this is taking a lot longer than I expected. So we'll see what I get through. So we want to show that the S-perp operator applied to EKK of 1 is this delta operator. We apply omega, right? And then we're applying the projection map pi k to k variables. And let me just show how this works in practice. I want to apply an omega. So getting notes out here so I can make sure I'm not making a mistake. Yeah, so in practice, what we actually do is, this is sort of what I was saying in response to Endon's question. You can expand one of these, just compute it straight out, by hand, group them into shear functions, or by computer, and apply omega, so that'll transpose all these s's, right? So you're keeping the t's and q's the same. I'm just giving an example so you can see what these polynomials look like. And you transpose all the s's. And then when you apply this S box perp, it's going to basically remove the inner left corner from each of these partitions. And so then we have these skew shear functions, which these ones are not straight shaped, so they decompose with the Littlewood-Richardson rule into a sum of straight shaped shear functions. And then you put that all together, and so that's going to be equal to this this omega of ek minus 1 ek. And so we'll have, if we put it together, for instance, we have an S21 here and also an S21 here, and you add those coefficients together. So we get 1 plus t plus q S21 plus, and then you combine the S3s from this coefficient and that coefficient. So this is just an illustration. Of course, I didn't tell you how to get the right-hand sides here, but just showing that, you skew one to get the other. But to prove this, so we're going to do it in k variables, and we need to go sort of outside lambda k here to a bit of a larger ring called the ring of symmetrical polynomials.
Do you mind if I'm going to ask you really quickly? So in that example that you just showed me, there's this capital E sub 4 comma 2. So here I should be reading it like 4 is the capital K, 2 is the
so this is
K. And I didn't really, okay, this was maybe okay, like I can't do everything in your hour talk, but you haven't really told me like what capital E sub KK is. It's in the elliptic-Hall algebra, but I guess like the point is that there's just some formalism, like it's known how to write these E sub KK of 1s in terms of shears. That's the point. Like we know
no,
that.
it's not.
Oh, okay.
No, that's what I was saying. I'm glad you asked this, because this is what Andon asked as well. And this is what I want to keep repeating this, because I'm saying that, this is an example for big K equals 4 and little k equals 2, which is actually n equals 3, little k equals 2, if you sort of unwind those formulas. And what we don't have is a formula for how to do this in general. You can just do this by computer, or even by hand in this case, actually, it's not too bad using the formulas that we have, either from the elliptic Hall algebra or actually just using the parking functions. You can write it all down, group it into Schur functions, and like check by hand that the skewing formula works, and it does in this case. And I'm just giving this example because this is going to be our running example of both of the
Right.
formulas throughout the whole talk. So yeah, just n equals 3, k equals 2. Okay, so but to prove this algebraically, we kind of go outside to the ring of symmetric Laurent polynomials, where we're allowing symmetric functions like x1 plus x2, but also things like this, where you're allowing the x1 and x2 to be in the denominator. So this is, we're going to use our example of k equals 2, just 2 variables for simplicity. And so now we're allowing things in the denominator. The basis is now Schur functions times a product of the product of the xi's to some negative power, basically. And so this is coming from GLK representation theory, where you have, you know, an irreducible representation times a copy of the determinant representation or its inverse. And this basically spans the whole thing, plus just the ordinary Schur functions, right? So the key sort of construction is this polynomial part. We're going to go outside, make these Laurent polynomials, and then show that these things are equal to polynomial parts of Laurent polynomials. And the definition here is, so if f is written in terms of this basis, and you have basically a sum of like some coefficients times s lambda over x1 through xk to the d power, plus a sum over, you know, just c lambdas, s lambdas. This is a generic polynomial in this Laurent polynomial ring. And f pol will just be sum of c lambda, s lambda. So this is, if you're going to learn anything from this talk, this is what I want to communicate, because it's something that took me forever to understand. And I know Jim and Anna and everybody else who has worked on this, it'll be obvious to them. But I hope that this will unconfuse you the way it unconfused me, which is this polynomial part is actually really unintuitive. In particular, if we take this example of f that we started with above, 2x1 plus 2x2 plus x1 squared over x2 plus x2 squared over x1. What is the polynomial part of that function? I thought for the longest time that it was 2x1 plus 2x2 because you throw away all the things that have denominators. But that's not how it works, because it depends what basis you write it in before you take the polynomial part. So what it means is sort of the GLK reps that don't have the determinant, meaning you write it in terms of Schur functions, or Schur functions divided by a product of the product of the variables to the d, and you only take the positive Schur functions that don't have a denominator. So let's actually just see how this works in this case. This s, if we're looking at the basis for two variables, and we're looking at f has degree 1 here, right? It's homogeneous of degree 1. So things like s3 divided by x1, x2 will have degree 1. And what this polynomial looks like is you write out your Young tableau, right? And there's 4 of them because we only have 2 variables, so we're allowed 1s and 2s, and they have to be weakly increasing. And so our Schur function is x1 cubed plus x1 squared x2 plus x1 x2 squared plus x2 cubed. And you divide that by x1 x2. And so what we're really getting is x1 squared over x2 from, you know, x1 cubed divided by these. Plus, if you do from x2 squared, it'd be the symmetric thing. And then we get an x1 plus x2. So our f above actually is this s3 over x1, x2 plus another copy of x1 plus x2. And x1 plus x2 is just another Schur function. It's a Schur function of a single square, right? So the polynomial part, actually now you cross off the stuff that has the denominator and you just take the Schur function s box, which is actually just x1 plus x2, not 2x1 plus 2x2. So that's how you take the polynomial part. And so that's the one of the key constructions in algebraic proof. Okay, so I'm going to start sort of just outlining now. So I think, you know, don't worry. I will post all these notes online and everything all filled out. And so you just sort of follow along. I'm going to go very quickly now because I've sort of, you know, introduced a lot of the key players. So what you do now is you can prove a lemma that when you take the inner product of f with the polynomial part of some Laurent polynomial g, you can extend the whole inner product, right? And take the inner product and, well, sorry, no, you're not extending the whole inner product. You're actually just reducing a Laurent polynomial to its polynomial part and taking the whole inner product with k variables. In k variables, here's the advantage. You can actually just say it's the constant term, the x0 coefficient, of f with the inverse variables plugged in times g with the ordinary variables plugged in. This is from GLK representation theory. And as a corollary, we can apply this s lambda perp k to an f by just basically plugging in the inverse variables in for the s and multiplying by f and taking the polynomial part. So this gives us a way, using that polynomial part formula, to just straight out calculate an s lambda perp in k variables applied to an f without having to expand f in terms of Schur functions. So now we've fixed that issue that Andon and Martha were both talking about. We don't know the Schur expansion, but it doesn't matter because we have this formula now, right? And so we can apply that instead. So the proof outline, there's a lot of sort of messy notation from BHMPS. I was going to try to do more of it. I'm not sure I'll have time now. But there's a symmetrizer sigma that basically you sum over permutations in SK of W applied to F over a product of basically you expand these denominators using the geometric series formula. So I'm imagining one of these like 1 over 1 minus xi minus xj as, 1 plus xi over xj plus xi squared over xj squared plus ... and you have this big Laurent series and you symmetrize it, and we're going to end up taking the polynomial part of one of these gadgets. So I'm not going to do any of the examples until I know I have time for them. We're also going to define this HQTK of f to basically be one of these symmetrizers applied to a formula involving lots of these geometric series expansions times our function f. Both the delta and rational shuffle are HQTs of things for k variables. So the things that we're borrowing from, that we're building off of from BHMPS and Mellet are these two formulas. So the BHMPS paper shows that in k variables, omega of the delta formula is HQTK of something complicated looking. And the other lemma is that I was gonna work through these examples, and I don't think I'm gonna have time. The other lemma is that from Mellet is that when you look at this elliptic Hall algebra, you can also express it in terms of HQTK of something over here on the right, take polynomial parts, and then we basically put it all together with a nice combinatorial connection lemma. And I think I'm just going to show the combinatorial connection lemma because it's fun. So I just want to show a couple little pieces of how we put it all together. So we have, skipping to the end, right, we have these two formulas in terms of symmetrizers over you symmetrize something to get a symmetrical Laurent polynomial. You take the polynomial part, and they differ. If you look at the stuff inside, this one has an hn minus k, and this one doesn't, and they have different powers on the x's. And the reason for that is the connection lemma now involves this rectangle and shows where this rectangle comes up for the skewing. So the rectangle that we're dealing with, again, is n minus k by k minus 1. And so we draw an n minus k by k minus 1 rectangle. And the lemma that we need is that if you plug in inverse variables, x1 inverse up to xk inverse, into the Schur function for the rectangle, then you actually get on the right-hand side a homogeneous symmetric function hn minus k of x1 through xk divided by the product of the variables to the n minus k power. So there's a GLK rep theory way of proving this, but there's also a nice combinatorial proof. So let me go through the combinatorics here. Schur functions, remember, are measuring Young tableau, and a Young tableau in a rectangle using only k variables with height k minus 1, well, if k equals 4 here, right, so it's height 3, then I'm only allowed to use 1s, 2s, 3s, and 4s. So my columns could be like 1, 2, 3, or maybe I could have a couple 1, 2, 3s, or it could be like 1, 2, 4, or it could be like 1, 3, 4, or 2, 3, 4, and that's all I can use. And they kind of have to be in that increasing order where the missing number, I'm going to draw it in a different color. This is just sort of an imaginary missing number. Each column is missing one number from 1 through 4. Right? So you can imagine sort of those missing purple variables at the top. And the Schur function term you would get from this Young tableau is, since we're plugging in x1 inverse up to xk inverse, the monomial we get from the red ones are x1 to the, there's 4 ones, so we do -4, right? And then x2, there's also 4 2s in this example. Oh, there's also 4 3s. But there's only 3 4s, right? So that would give you a term on the left-hand side that's like x1 to the -4 times x2 to the -4 times x3 to the -4 times x4 to the minus
But that's the
2.
same as like if you take the missing numbers and divide by.
Exactly. So actually, I'm gonna put this denominator on the left-hand side and multiply by it, right? So if we multiply by x1, in this case, n minus k is 5, right? x1 to the 5th, x2 to the 5th, x3 to the 5th, x4 to the 5th, then what we're getting here is x1, x2, x3, x4 squared, which is exactly the purple content, right? It's the missing numbers, and that's one of these terms from the hn minus k of x1 through xk. So you match up the terms on the left-hand side and the right-hand side, and it's just a very pretty combinatorial lemma, and it's exactly what you need to sort of put together this formula with this one, apply the perp operator, and remember the perp operator essentially is applying one of these s's with the negative variables, the inverse variables plugged in. And so you put all those lemmas together, and we, this summarizes the proof of the skewing formula, just showing that both of these formulas have the same inner product. Both of these formulas have the same inner product with any Schur function. And that's sufficient because the Schur functions form a basis. So I know I went really fast now. It's 10:52. I just wanted to get the outline done. And now I can sort of ask the audience if there's either questions or specific examples I should go through of, like, I could go through what these HQTKs actually mean because I have examples prepared, but anything anybody wants to ask is fine.
Can I ask a quick question?
Yeah.
Can you repeat how you got the exponents, the negative exponents for x1 through x4 in that example you just did again?
Yes. So I kind of skipped a step. So let me zoom in and erase it. So what I would normally do if it was S of this rectangle of x1, x2, x3, x4 without the inverse plugged in, what this would give you is a term in this, the same way we were doing the monomials from the parking functions and from the Young tableau for the Schurs, we take x1 to the number of ones, right? So how many ones are there here? 1, 2, 4. 4 x1s. And then we have 1, 2, 3, 4 x2s, and then 4 x3s, and 3 x4s. And then I'm plugging in x1 inverse, x2 inverse, x3 inverse, x4 inverse in for these variables. So I actually just negate the exponents, right? x1 to the minus 4, x2 to the minus 4, x3 to the minus 4, x4 to the minus 3. There we go. Yeah, thanks for the question.
Yes, thank you.
To follow up that question on this particular example, I totally missed what the significance is of the purple numbers on top.
Yeah.
And
So the
where they
purple
are
numbers
coming
are the
from.
complement of the columns below them. So we're doing a height k-1 rectangle, and we only have k variables. So each column contains all but one of the numbers. And so the purple one is just the one that's not in its column. So I'll say, so purple union red in any column
should be
is 1 through k, right?
Thank you.
Because if we put that invisible purple row, then it's height k, and that's all we have. So yeah. Other questions? By the way, organizers, was I supposed to stop at 50 after or an hour?
Well, I wanted to mention that in general, you can feel free to give a lecture until 1, and then you can have a question and answer period, and people can stay for that or leave as they choose.
Oh, okay, great. So, well, then maybe I'll fill in a couple of the details up here, because this is connecting back to the same example, the running example that I said I wanted to sort of go through. So I wanted to, now that we understand this polynomial part formula, because we did the example with the f, we can look at what this formula means, and in an example, and just work out what it gives us. So the formula, sorry, I'm going to my own notes. Okay, here it is. So this formula says that, so for k equals 2 and n equals 3, we're doing the k variable version of omega applied to delta E1 prime E3. And so on the right-hand side, we would have HQT2. And on the top here, we have just x1 and x2. And then Hn minus k, what is n minus k? N minus k is 1. So h1 of x1 and x2 is just x1 plus x2. And then on the bottom, we actually have the product over all I that makes sense of 1 minus qt xi over xi plus 1. We only have two variables, so we're only going to have x1 over x2, basically. So somehow when you reduce it to two variables, a lot of this feels much more tractable, and you can actually compute with it. So this is basically a symmetrizer sigma applied to, we're now just plugging in the definition of HQTF, right? So I'm just plugging this definition of what it is a symmetrizer of, and it's a symmetrizer of x1, x2. There's something that cancels this denominator from the definition of HQT. So what it actually ends up being is you're dividing by just two products in the denominator. And taking the polynomial part. Oh, and I forgot the polynomial part up here. So what you would really do is expand these out into a big Laurent series and take the coefficient of some q or some t power and take the polynomial part to see what that coefficient is. But let's just do sanity check, which a very easy sanity check to check is q equals t equals 0. How do we compute the Schur function for the constant term where there's no q's and no t's? Well, now this goes away and this goes away. So actually it's just sigma of x1, x2 times x1 plus x2.
What does the sigma mean?
So sigma is this symmetrizer we had upstairs. Oh, and I could just do this example first and then we'll see. So if I was going to symmetrize x1, then I would, and k equals 2 again, then I would sum over all w in S2 of x1 over 1 minus x1 over x2, right? And what that sum over, since we only have identity and the transposition 1, 2, what this is really is x1 over over that, and then you switch the x1 and x2. Right, so you just apply the permutation, meaning switch the 2 and the 1 on both of them, right? And so you can expand this out using the geometric series formula. So this is like x1 times 1 plus x2 over x1 plus x2 squared over x1 squared plus dot dot dot. And then you have x2 times 1 plus x2 over x1.
Oh, so it's infinite.
Plus. Yes, it's infinite. And that's why it's important that we're taking the polynomial parts in the actual formulas. Right, so these are infinite Laurent series, and you're actually doing sort of 2x1 plus 2x2 plus, then we have one copy each of x1 squared over x2.
And so on.
And so on, yeah. Right, and you'd have x3 squared, not x3, x1 cubed over x2 squared, and so on, right? All symmetrically. So basically all the degree 1s show up, and you have two copies of x1 plus x2 because you have sort of the copy x1 from this one, and then also, oh, sorry, I screwed up on the left. Sorry, on the right, hang on. These should be x1s over x2s. There we go. Oh, maybe I expand. Oh, no. Maybe I expanded this wrong. Well, it's whatever series this turns out to be. Okay. I think I had the example of sigma x2 before, and that came out to something different. So yeah, I mean, you can combine the terms. We have an x1 and an x2, and then we have like x1 times x1 over x2. So we would have an x1 squared over x2 and so on.
Yeah, I want to add one thing. Sorry.
Yeah.
It's just that like the reason that we have this is because when you have like the sigma, like you may ask like why do you define something that weird? The reason is because if you apply sigma on x to the power, which is a partition, you get back a shear function when you take the polynomial part. And also it allows you to very easy to stricken the shear function. So basically you can think about this sigma is just like another way for you to get the shear function. And if you apply to x to any partition power, you get back exactly the shear function. If you have like x to a power, which is not like what do I mean by x to a power of a partition is like x1 to say power 3, x2 to a power 1, x3 to power 1, and so on. If you have like x1 to the power 1, x2 to the power 3, and you apply to this, you actually either would get 0 or another shear function with a sign. So this is a way to describe shear function, basically.
Anna, is what I wrote in the box over there correct?
Yes.
Okay, so what Anna's saying is that if you take sigma applied to x lambda, which means x1 to the lambda 1, x2 to the lambda 2, right, up to x k or xr to the lambda r, whatever it is, and take the polynomial part, then you actually just get the shear function s lambda. Yeah, and those I think are not exactly what we're applying the sigmas to, but it's true that when you take the polynomial part, the shears that you want are going to come out. And so, yeah, thanks, Anna.
Yeah, I understand that like it is kind of weird that like why do you define something like this without any reason, right? Like that's kind of weird, but they do have like a reason behind all these.
Right. Thanks. Oh, there's messages in the chat. Oh, bye, Martha. Okay, yeah, so we're definitely at the end of the hour, so I'll just pause here, and if people want me to continue the example, I can.
Well, first, let's thank Maria for a great intro here.
Thank you so much. Yeah.
And
excited.
yes,
Bye.
any questions? Further discussion?
There will be combinatorics on Thursday.
There's a chat question.
Oh, another chat question. Is there something to do, is it with Vandermonts for that symmetrizing and polynomial part formula? I think I would ask the experts. I don't know. Anybody know? Oh, Vandermont's meaning like, I would think an anti-symmetrizing would be Vandermont's, right? I mean, Vandermont determinant I think of as like x1 minus x2 times x1 minus x3 times x2 minus x3. And the Vandermont is sort of the sum of, like it's a sign sum, and I don't think sigma is really a sign sum. So I don't think you would get, this is sum of sine of sigma you would apply this to x1 squared x2 or something like that, like some, the leading term, if you anti-symmetrize over all permutation sigma and s3, then you would get the Vandermont. So I don't think so. Wait, but Jake is clarifying sigma of x lambda, Paul, is s lambda. Reminds me of the ratio for s lambda. Oh, the formula for s lambda is a ratio of determinants. Oh, maybe. Well, but the ratio of determinants is again an anti-symmetrized thing over an anti-symmetrized thing. So yeah, Anna says no, you do not. Was that in response to Jake or Jason?
Oh, Jason. But
okay. Do you get the McDonald polynomials?
Well, I mean, depending on which McDonald polynomial, but even
Right.
like even if it is like the modified one, you still have to do something. So it's not like exactly that easy, but there is something similar to that, but you can get the Hollywood to apply to that. So yeah, so like all these things, like you can actually get the right set and then you can get the polynomial that you want. So like just going back to the Vandermonde, you can think about like the bottom part is kind of like it, but it's not really like ratio of the determinant, because like basically what you're trying to do, like you can see that like the I and I+1, we have a way to talk about reset, and you're taking the full root ideal because you're just doing like I less than like K, so everything is a root ideal. So if you take everything that's like applying to the right operator, then you get the Hollywood. If you apply like the empty one, then you get like sorry, like depending on what I mean by empty or like full reset. But one complement gives you the Hollywood and the other one gives you like the shear function. So this is kind of like a nice technique to link your shear function to the Hollywood. And also, of course, you have like a further generalization to modify the Madonna polynomial as well. But things in between are getting like interesting, because like what is, when you go from one to the other one, what's going on? Now go to the Vandermonde is like you take the full thing, and then the bottom part is kind of like that, but like not always, because it really depends on the choice of your reset.
Yeah, thanks for answering the questions. This is, I mean, I think, I hope it was clear from this talk how much we stood on the shoulders of giants, because it was all, you know, this work in these other papers that we just sort of put together. Right? So yeah, I would know a lot more about the polynomial part and the sigma operator. Okay.
Okay, well, I guess we're done for today. Well, let's thank Marie again, and we'll see you on Thursday.
Yeah, I can send you guys like the full notes as well. So
We'll post those on the webpage, the IPAC webpage.
so I can post one with the examples filled in and one without. So if you want to work out an example on your own, you can. So I left those blank.
Perfect. And Anna will post we'll post the video link as well on
Okay,
YouTube,
great.
which will be available later today.
All
Okay, see you
right.
all on
Right.
Thursday
See
then.
everyone
Hey,
on
Bye.
so long.
Thursday.
Thank you.
Bye.